Now let's move on to the next set, from 7 till 14. Okay, so what are we asked here? Show that a function is a solution of the given differential equation. Show that this is a solution of this. Show that this is a solution of this. So we're not asked to solve. They're giving us the equation, they're giving us the solution, and they say, show that it works. Can we work on 11? Is that okay, or you want to choose another?
11 works.
Okay, so let's work on 11 then. On 535. So we are given y equals negative 2 e to the x plus x e to the x. So this is a solution. It's a function, right? Is a solution of this equation. How do we call this equation? The second derivative minus 2 times the first derivative plus y equals 0. So what type of equation is this?
Separable?
No. You'll see when we get to separable. Not yet. This is a differential equation. It has the second derivative, it has the first derivative, it has the function. How do I show or check that this verifies the equation? What should I determine first? What I don't have. This I have. But I don't have the first derivative and I don't have the second derivative.
First, we have to find our first derivative, and then after that one, find our second
Excellent.
derivative.
Excellent. Can anyone differentiate this for us?
Negative 2 e to the x.
That's it. Perfect. Plus. Careful. First function, second function. Product. Can anyone help with this?
Plus 1,
So
Just
you
plus
mean e to the x, yes, plus.
and then plus x dx.
Excellent. Since these are combinable, they are like terms, I'm going to write negative 2 e to the x plus e to the x as negative e to the x plus x e to the x. So now I have this. I have this piece, I have this piece, but now I need this. Can anyone help with the derivative of this function? Because we need the second derivative. Because that's what I have in the equation, in the differential equation. I have the second, I have the first, and I have the function. Can anyone differentiate this?
Negative e.
Excellent. Plus. And I know you're going to say, we just differentiate this, just copy it from here. First function prime times the second plus the second times the function prime, the second function prime. So I'm going to copy it from here. It turns out that these two go away, and this is x e to the x. So this is one piece, and this is the other piece. Now, I will replace, I go back to the original differential equation. I will replace the second derivative. Okay, done. Minus 2 times the first derivative plus the function. And now, if this equals 0, then I'll go back and say yes. If this does not equal 0, I will go back and say no, it's not a solution. So, x e to the x plus x e to the x, 2x e to the x. Negative 2 times negative 1 is positive 2 e to the x. Negative 2 times x e to the x, negative 2 x e to the x, minus 2 e to the x. So what is the answer?
0.
I go back and say, yes, it is a solution of the differential equation. I checked. I did exactly what it was telling me to do. I found the derivative, the first derivative, the second derivative. I put them correctly step by step. I calculated all this and I got 0. If I got 0, then it is. What if I had gotten 5 instead of 0? What would you have said about y equals such and such?
It's not a solution.
Yes, because 5 cannot equal 0. Perfect. So what have we studied so far? Basically, a review of chapter 4 to find the antiderivative, and we were given an initial condition, so we found the unique solution. What is the other thing that we discussed? Once given a differential equation and a function, we can be asked, is this function a solution of the differential equation or not? So these are the 2 topics so far. Okay? Can we move on? Okay, so before I let you choose, I would like to choose the next set. So we looked at everything till 14. They're all the same. We can choose others. We can go back and do that. Find the general solution of each differential equation and check the solution by substituting into the differential equation. So let's select a problem from here. I know it looks weird.
$16.
16. So let's look at 16. Perfect. So in 16, it's still on page 535, we have dm over dt equals 0.05 m. Perfect. Okay. This is something called a separable differential equation. What does this mean? It means separate the variables. Okay, what does that mean? What do I separate? Okay, I want to separate m from t. I know this notation is confusing because we already talked about this. This is m prime. So m prime is the same with dm over dt. True, but right now we really want to have m on one side of the equation and t on the other side of the equation. So we are separating these two. It still has the same meaning, but we can also separate them. Okay, now, first of all, I recommend let's multiply both sides by dt. No problem. So dm equals 0.05 m times dt. So I have a constant on the right and I have dt on the right. I have dm on the left-hand side, but I also have m here. I don't want m to be on this side. I want m to be on this side with dm. What should I do to both sides to make m disappear from the right-hand side and appear on the left?
Divide by m.
Of course. We are dividing both sides by m. Awesome. So dm over m equals 0.05 dt. Now, remember what we did last time. And I keep going back to all these situations so you can connect the dots. So last time we had this equation, the demand equals the supply, 5 minus x equals the square root of x plus 7. What did we do to both sides to solve for x? We applied the inverse operation of the square root. So now I want to solve this. I see a derivative on this side and I see a derivative on this side. What is the inverse operation that has to be applied to both sides? to the derivatives.
Is it the antiderivative?
Yes, but at the same time, we are integrating both sides. Excellent. Integrate both sides. Yes, I know this is totally new. From this point on, everything is new in this particular type of problem. We have not seen this before. We never really applied integration to both sides. We did it, but we didn't really emphasize it. Good. So now don't look on this side. Don't look to this side. See, that's why I have all these props. And tell me what to do with this. The integral from dm over m. Which function prime is 1 over m?
ln of x.
Yes. Don't forget the absolute value, please. It's not ln, but it's natural log ln of natural log. Okay, perfect. Now don't look on that side and tell me what to write here. Which function prime is this?
It's 0.5 t squared over 2.
But t squared over 2, when I differentiate, I have a t, but there is no t here. Which function prime is 1?
T.
T, plus a constant c. From this moment on, it's algebra. Okay, we have to solve for m. So let's summarize what we just did. We were looking at this equation. We were asked to solve. It's a differential equation, right? It has a derivative equals something with a function. So we are separating the variables. By separating the variables, first of all, we realize that we have to multiply both sides by dt, and we did. This is okay to be here, this is okay to be here, but this is not. This has to be somehow connected to the other side. And perfectly you said, divide both sides by m. Fine, I did. Now, m is alone on one side with its dm, and t is alone on one side with its dt. We are allowed to integrate both sides, and we did. The left-hand side is natural log of the absolute value of m. When we calculate this indefinite integral, we get 0.05t plus a constant c. If you differentiate, you get that. Now, from chapter 3, we have to be able to solve for m. So this is all algebra. From this moment on, there is no calculus here. What is the base of natural log? I don't see a base, but we know what it is. What is it?
N.
E, right? So, how do I solve this equation for the absolute value of m? Anyone remembers what happens here? How do I write
It's going to be 0.05.
e raised to this power equals the absolute value of m. E raised to 0.05t plus a constant c equals the absolute value of m. Let me refresh your memory. So if we have log base b of x equals y, b raised to y equals x. B raised to y equals x. I'm going to write it again here so everyone can see it. B raised to y equals x. Okay? So b raised to y equals x. Okay. Now, also remember when we have a base raised to a sum of two quantities, this can be rewritten as e to 0.05t times e to c. I can go back, copy the base, and add the exponents. So this is the absolute value of m equals e to 0.05t times e to c. This is considered a constant. I'm not going to use c, I'm going to use c1, so it's not confused with that. So the absolute value of m equals plus or minus, because that's what the absolute value means, a constant C1 times e to 0.05 t. So this is our first differential equation. This is the first time I'm pushing my computer further a little bit. So this is the first time we solve a differential equation that is called separable. What we started with a few minutes ago was just finding the function using chapter 4 basically. But here is the next level. And we are not going beyond this level. There are other types of differential equations. We're only looking at the simple ones. Simple, nothing, just chapter 4, or separable differential equations. Let's choose another. Okay? Find the particular solution of each differential equation as determined by the initial condition, and check the solution by substituting into the differential equation. Oh, we forgot to do that here. They're asking us to do the same thing. So let's differentiate.